Alright, so this is lab 2. And this time we're going to be looking at an object in free fall, and we're going to create models of the object's motion and compare them. The physics concepts to keep in mind are that the net force is not equal to 0, so the velocity is changing due to Newton's second law, force equals mass times acceleration. The motion in free fall is only going to be in one dimension, it's going to be the y dimension. It's going to be moving in the negative y direction because it's falling. We're keeping the plus y axis up. Forces to consider are force of gravity, of course, but also drag force. And so these will be important later. Here's tracker. I observed a person in a dorm dropping a tennis ball. I picked 1.8 meters for the calibration, which was the height of the person in the dorm. I set the axes to the initial point of the tennis ball when it was in the person's hand. And I used the center of the tennis ball as my point of mass. You can see the graph here and the data. And here's a better look at the data. And I used the initial position and the final position to calculate velocity, but that doesn't really tell us much because the velocity is changing. I calculated the acceleration, which is negative 9.75 meters per second, which is really close to negative 9.8 meters per second, which is the acceleration due to gravity. However, it may or may not be that close, or may or may not be that close, or it should not be that close, I should say, because of drag force. So here's the code. We have the equation for weight in the loop. Time is less than 0.568 seconds. That's the duration of the tennis ball falling. We have the Newton's second law equations for velocity and position. Ball's mass is 57 grams. Initial position and velocity are 0. You have delta t, gravity, j hat, which is unit vector of the gravity. You also have b equals 0 because there's no drag force being considered in this first part. The model's in the bottom, of course. Model versus experiment graph. This is the first one, which just has the model position with no drag. And we notice that, for the most part, the experimental position is a bit lower than the model position. Which really shouldn't be, because this is not considered drag. So the experimental position experiences drag, so it should actually be progressing less in the y direction than the model position. Now, what are some explanations for this error? The tennis ball might have accelerated too quickly in the beginning due to the interference of the person dropping the ball. Choosing the center of mass can also be kind of difficult because the tennis ball being a blur in some frames. So now we actually have to consider drag force. We found B to be 0.0009 by equaling the final point of the model to the final point of the experiment, which was y equals negative 1.571. So we put in the drag force equation to our loop this time, and there should be a drag force there, but it's not noticeable because B is so small that we found. So this is our model versus experimental graph 2, and this has the experimental position and the model position with drag. And we notice between the two model positions that they're really hard to distinguish from each other because B is so small, so the drag force really doesn't do much. Now, it really shouldn't be that close because drag should honestly be pretty significant due to the fact that the tennis ball being, has a bit of surface area. So again, some sources of error include inconsistency, inaccuracy in the points of mass, because the tennis ball blurs. Initial velocity of the ball, extra acceleration due to the force of the ball being released are also possibilities. Also distortion. I mean, having the ball drop far away from the viewing of the camera can also cause problems, so that is to be considered. Comparing velocities, just has the velocity with or without drag, and so we have to consider which one would have terminal velocity. And we can automatically rule out that the model velocity without drag is not going to have terminal velocity because gravity is the only thing acting on it, so the velocity is going to constantly increase in the negative y direction. The model velocity with drag eventually will have terminal velocity. Now, terminal velocity is basically where the force of gravity is equal to the drag force, so the velocity is not changing because F net equals 0. So if you look at the math at the bottom of the graph analysis, you should see that yes, the model velocity would drag. Theoretically, if b was actually bigger, not due to our error, it should actually reach terminal velocity, which means that the blue line in this graph should probably plateau at some point. So how does having initial velocity affect the terminal velocity? Again, here the fact is b is so small, so it's not going to reach terminal velocity unless there's a really, really high initial velocity. But the thing is, since drag force is proportional to the velocity, the fact is if you have an initial velocity, then that will speed up the amount of drag that you get on your object, and so it will actually reach the terminal velocity point faster, and that is also explained at the bottom in the graph analysis. All right, that is it.